This video lecture provides an introduction to biomechanics. The lesson focuses on the overlap between biology and engineering through an explanation of physics of the human body as it relates to motion and balance. Support for the development of this lesson has been provided by the National Science Foundation through the Ohio University Boat of Knowledge in the Science Classroom program. First, stand up and give it a try. Do a regular push-up, and then do a girl push-up where you rest on your knees instead of your toes. Which is easier? Now try walking on your tiptoes, then walking on your heels. Which is easier? Next, try to lift something while keeping your arms straight, and then try to lift the object with your elbow bent. Which is easier? Finally, stand up straight, lift one foot off the ground, and try to bend over. Why does staying balanced get more difficult? We'll find answers to all these questions as we progress through this lesson. The body can be considered a mobile physics lab. If we look at the body, we find motion and balance, fluids and pressure, energy, acoustics, optics, and electricity. Which parts of the body do you think correspond with each of these concepts? In this lecture, we will only focus on the topics of motion and balance. Let's look at the body from an engineering perspective. If we were trying to define the function of parts of the human body using engineering terms, what do you think the bones and muscles are like? The bones and muscles are like a structure or machine. They provide support and enable movement. What about the heart, lungs, and vascular system? These parts of the body are governed by laws of fluids and pressure. What would the brain be like? The brain acts like the computer, sending and receiving signals to give and interpret instructions. Then what would the nervous system be? The nervous system provides the electrical connections that deliver and retrieve information for the computer, or the brain. Let's see how our bodies compare to engineered objects like structures, machines, and computers. Look at these 7 statements and decide which you think are true and which are false. Once you've made your decisions and marked the ones you think are true and false, we'll discuss each statement. Human bone is 5 times stronger than steel by weight. True or false? This is true. When comparing steel and bone strength by weight ratio, bone is stronger. Next, the human brain can process 100 trillion instructions per second, while the best computers can only reach millions of instructions per second. True or false? This is also true. The human brain is far more robust than even the best computers that are available. Next, a cough clocks in at 60 miles per hour, while a sneeze is around 100 miles per hour. True or false? That's true. So Mother was right when she scolded you for holding in your coughs and sneezes. In fact, the sneeze is so powerful that all of your organs temporarily shut down, which is why you can't keep your eyes open when you sneeze. Your body gives off enough heat in 30 minutes to boil half a gallon of water. True or false? This is also true. Your body is constantly turning food calories into energy and producing heat. We are about 1 centimeter taller in the morning than in the evening. True or false? True. If you measure yourself in the morning, you're slightly taller, because sleeping horizontally allows your vertebrae to separate after spending all day in a vertical position, with gravity pulling down and scrunching them closer together. The human heart creates enough pressure to squirt blood 30 feet in the air. True or false? Once again, this is true. The human heart is an incredibly strong pump that pushes blood all throughout your body and never rests from the minute you are born until you die. Finally, muscles can only contract, so they come in pairs. True or false? True again. Muscles are either relaxed or contracting, but they never go beyond the relaxed state, so pairs of muscles contracting in opposite directions are necessary to give us the wide range of motion that we have. There's no doubt the body is pretty amazing, especially from an engineering perspective. Our best efforts after years and decades of research can't even come close to the body's abilities. The musculoskeletal system is the structure and machine that provides balance and motion. The functions of the cardiovascular system, like breathing and pulse, are governed by laws of fluid and pressure. The brain is a computer with an electrical connection called the nervous system. We'll be focusing on the musculoskeletal system in our lesson. The musculoskeletal system includes muscles, tendons, bones, and joints. Muscles generate force. Tendons transfer the force to the bones. Bones move if enough force is transmitted. Joints allow bones to move. In biology, these components form the musculoskeletal system. In physics, these components form a system of simple machines. Let's talk briefly about simple machines before we discuss how they relate to the musculoskeletal system. What is a machine? A machine is anything that increases mechanical advantage. Machines function in one of four ways. They can balance multiple forces, enhance force, enhance range of motion and speed, or alter the direction of the applied force. The musculoskeletal system uses three types of simple machines: levers, wheel axles, and pulleys. Can you think of some examples of levers, wheel axles, and pulleys in the body? A lever is defined in physics as a rigid bar that rotates about a fulcrum in response to an applied force or effort and a resistance load. Try to relate the parts of a lever to the body. In the body, the rigid bar is the bone. The fulcrum is the joint. The force or effort comes from the muscle. And the load comes from weight or external objects that are being supported. There are three classes of levers that are defined by the ordering of the fulcrum, effort, and resistance. For first-class levers, the fulcrum is between the effort and resistance. A good example of a first-class lever is your head. Think about when you nod your head. Your head pivots about your spine, which is the fulcrum. The muscles in the back of your neck are providing the effort to counteract the weight of your head in the front, or the resistance. Second-class levers have the resistance between the fulcrum and the effort. This is like your lower leg when you're walking. You pivot around your toes, your weight is acting down through the front of the leg, and the effort is coming from the calf muscles. Third-class levers have the effort between the fulcrum and resistance. When you're holding something in your hand, your arm is acting like a third-class lever. The fulcrum is at your elbow, the effort is coming from your biceps, and the resistance is in your hand. Classify these four actions as one of the three classes of levers. Think about the locations of the fulcrum, effort, and resistance while you classify them. Let's start with nodding your head. The fulcrum is at your spine, the resistance is coming from the front of your head, and the effort is coming from the back of your neck. Fulcrum between means it must be first class. Now let's consider lifting weights. The fulcrum is at your elbow, the effort is coming from your biceps, and the resistance is in your hand. When effort is between, it's third class. What about walking? The fulcrum is at your toes, the resistance is coming down the front of your leg, and the effort is coming from your calf muscles in the back of your leg. Since the resistance is between, it's second class. Now what about doing a push-up? Let's try to visualize what happens while doing a push-up. When you go up and down, you're pivoting about your toes, so we'll place the fulcrum at the toes. The weight always acts at the center of gravity, which is at the middle of the body. This is where we'll place the resistance. Finally, your arms are pushing you up, so this is the location of the effort. Resistance between fulcrum and effort is the definition of a second-class lever. Now we're going to move on to another concept that will help us to solve problems and complete the lab activity associated with this lesson: torque. Torque is defined as the force times the lever arm distance, so it has units of Newton meters or pound-feet. Torque is a rotation about a particular point. The rotation is assigned a sign convention, with counterclockwise rotations being positive and clockwise rotations being negative. Let's use this diagram to define the torques and solve for the force the biceps must provide in order to hold this book. Let's start by deciding which point we want to take the torques about. The arm is in equilibrium, so the sum of the torques about any point is 0. Remember that we ultimately want to solve for the force Fb, so we need to be wise when choosing which point to sum the torques about. We have 4 forces and 2 are unknown, Fb and Fe. So we should try to pick a point that will eliminate the unknown Fe from the summation. We will use the point E at the elbow as the point about which torques will be taken. Choosing this point eliminates the unknown Fe. Take a minute to think about why this is true. The unknown force is eliminated because the torque due to Fe about point E is 0, since the distance from point E to the force is 0. Now we can begin writing the torques associated with each of the remaining 3 forces. The torque due to force Fb equals Fb times 0.04 meters. Remember that even though we are given the distances in centimeters, we need to convert them to meters to complete the calculation. The torque due to the weight of the arm, Wa, equals weight of the arm times 0.16 meters. We're given mass of the arm, so we can calculate the weight of the arm, knowing that weight is mass times acceleration due to gravity. Substituting in the values of m and g, we get the torque about point E due to the weight of the arm to be 3.9 Newton meters. Similarly, the torque due to the weight of the book is mass of the book times g times 0.38 meters. Substituting in the values and solving, we get the torque about point E due to the weight of the book to be 14.9 Newton meters. Now, to solve for Fb, we need to write the sum of the torques about point E and set equal to 0. When writing the sum of the torques, we need to remember the sign convention that counterclockwise rotation is positive and clockwise rotation is negative. Force Fb will cause a counterclockwise rotation, so torque Tfb is positive in the equation. Force Wa will cause a clockwise rotation, so torque Twa is negative in the equation. Force Wb will also cause a clockwise rotation, so torque Twb is also negative in the equation. If we rearrange the summation to solve for Tfb and substitute in the values we know, we can solve for Fb and find that the force exerted by the biceps to hold up this book is 470 newtons. We noticed from the example problem that all torques acting about a point should sum to 0 for static conditions. But what determines how much force is needed to counteract a resistance load? Try holding a book in each of the 3 positions shown in the figure. Which seems to be the easiest? You probably noticed that holding the book in the position on the right is the easiest. This is because the amount of force needed to counteract a resistance load depends on the resistance lever arm and force lever arm. When your forearm is parallel to the ground, like the picture on the left, the resistance lever arm is very large compared to the force lever arm, which means that the torque due to the resistance will be high and will need a large force to compensate for the large torque. When you hold the book in the position shown on the right, the resistance lever arm is not much larger than the force lever arm, so it doesn't require as much force to be exerted from your muscles as the position on the left. The concept of torque applies all throughout the body, not just at the arms. That's why Mom was right when she told you to stand up straight and not slouch. Good posture, like that shown in the left picture, is key for the body to transfer forces along the spine. Poor posture, like the image shown on the right, creates torque around the hips, which forces muscles in the back to react with large forces beyond the force they were meant to exert. Now let's look briefly at wheel axles. Wheel axles are less common than levers in the body, but they allow for greater range of motion and speed. The outcomes are different depending on whether the force is applied to the axle or the wheel. Can you think of an example of a wheel axle in the body? The shoulder joint is one example of a wheel axle. In this case, force is applied to the wheel, which amplifies the force. This happens when we throw a ball. In this case, what would you label as the wheel and the axle? The wheel is the forearm, and the axle is the humerus. This wheel-axle action allows us to throw things far and fast without much effort. Another example of a wheel axle in the body is the rib cage. In this case, force is applied to the axle to amplify movement. This happens when the spinal muscles act on the vertebrae. What would you classify as the wheel and axle for this case? The wheel is the rib cage, and the axle is the vertebrae. This wheel-axle action allows us to twist. Now we'll consider pulleys. There are only 2 pulleys in the body. What do you think they are? The patella and the lateral malleolus are pulleys, meaning they change the direction of the applied force. The lateral malleolus is located in the ankle and allows for plantar flexion when the peroneus longus contracts. When the peroneus longus contracts, the force is in the upward direction, but the lateral malleolus changes this to a horizontal force on the bottom of the foot that enables us to walk. In a similar manner, the patella allows the quadriceps to pull up on the tibia, which also helps us to walk. Stand up and try walking without bending your knees and only bending your ankles. Now try walking without bending your ankles and only bending your knees. Then walk normally. Do you notice how these 2 pulleys working together provide us with ease of mobility while walking? We discussed motion in great detail, so now let's talk about balance. How is balance maintained, especially in these cases? Balance occurs when static or dynamic equilibrium is achieved. Equilibrium means there is no change in speed or direction. Balance is related to our center of gravity. By walking, we are constantly putting our body in and out of balance. Where is our center of gravity? The answer is, it depends. Center of gravity differs with gender and age. Center of gravity is the location about which weight or mass is evenly distributed. Children have a high center of gravity because their heads are typically large in comparison to their bodies. This is why children are usually unstable while walking. Women's center of gravity is lower than men's center of gravity because women generally carry the most weight around their hips, and men carry the most weight around their chest. Center of gravity also changes with position and load. The center of gravity for the man holding the child is higher and slightly towards the back. The center of gravity for the man holding the bag has shifted more towards the side that is supporting the bag. The center of gravity for the woman holding the books has shifted forward. Sometimes our center of gravity is outside our body. Remember that center of gravity is defined as the location about which weight of mass is evenly distributed. If we were to do a handstand like the picture on the left, our center of gravity would be directly below our chest, and therefore outside our body. Since balance is related to the location of center of gravity, what location of center of gravity do you think gives us the best balance? We achieve the best balance when the center of gravity is near the center of the base of the support and when it's lower. This explains why it's hard to stay balanced when standing on one foot and leaning forward. Your center of gravity is no longer centered over the base, which would be your feet. To increase your understanding of the biomechanics topics we just covered, you can complete the following activities that are included as part of this lesson. In the first activity, how strong are your muscles, you can determine how much force your biceps and deltoids exert while holding books. The second and third activities are connected. These activities take the biomechanics concept one step further into the realm of prosthetics, where you will design a prosthetic device and build a working model of your device.